Like I've shared that collection. Has any of you seen it?
Yeah, I have just seen.
Okay.
Like where have you shared where I can find it?
You can find it either in the OMC or I'll share a link of a collection of my handouts.
Actually, I saw your handouts online, but they were asking for some Dropbox account or something like that.
The link is a Dropbox link. I don't think you need an account though. You can bypass it. Like there's just an option to cross it or something.
Okay.
Yeah, okay. So before we start, there's one thing I want to say. Some people had a slightly adverse reaction to the doubts that were being asked. Please don't do that again. The If a person is asking doubts, that's a good thing. Do not give the kind of reaction that was given, and there's nothing wrong with asking doubts. And I'm pretty sure that there are still a few details that not many in the last meeting who even made the comments can work out that easily. So please don't make such comments. It's good that he's asking doubts. It's good that if anyone is asking doubts, please don't do that. Okay, now comes arrows. Let me also open GeoGebra once.
GeoGebra? Like, is arrows a topic of geometry?
No, just for visualization.
Okay.
Okay, so arrows is just essentially a way of thinking about certain structures.
You can't see your screen.
Oh, sorry, I thought I was sharing. My bad. Fine now?
Yeah, we can see it now.
Yes. Okay, good. So the arrows is essentially a way of visualizing certain structures. Things we think about using arrows include also arrows is not a formal thing that you'll write like draw an arrow here, draw an arrow here. It's just something for you to for a way for you to think about a certain structure. So we can think about iterated FEs this way. We can think about some types of permutations this way. We can think about
By iterated FEs, you mean f of, right?
yeah. We can think about some combine or some grid type structures, etc. Let's begin with an example. Let me just copy the problem once. Yeah, okay. Okay, so any of you who has done this problem, I think many of you would have seen it before. It's a very famous problem.
Yes, I have seen it in some lecture before.
Okay, that's fine. Others?
I've seen it, but don't know the solution.
Yeah, I saw it, but I forgot like everything.
Yeah, and I also think that it requires some Billsworth theorem.
No. I think you attended the MOOC lecture and I think you're just merging stuff. Okay.
Who's like,
MOOC or probably maybe the INMO TC one, which I think Yash Sanjeev's lecture included this. Okay. So now that we are looking at this, okay, how do you think we can think about this? Anybody?
We have to prove that F is a bijection basically, right?
No. It says f of t is equal to t.
this means
On
f
the
of
set, on the set T, it is a bijection, not on the set S. It's a bijection on the image. It's not necessarily a bijection on the original domain.
also T is a set, right? Or not?
Yes, T is a set. So f of t just means the f of every element of t. And that also generates a set, right? That set must be the same set. That's all it
So,
means.
so we have to prove that. So we have to prove that F is bijective over T.
Yes.
Okay.
Okay, somebody already gave a very useful idea in the chat privately. So they say, let's try g equal f to the n. Now, if we do this, then our equation becomes that f to the to n
G
plus
not
1.
necessarily like f to the power n not necessarily be in the set n.
What?
Like it is not necessary that f suppose f of n belongs to a, right?
It's not necessary that f of n belongs to a.
I mean like the function f square belongs to a. So like we cannot.
Why not?
F
Suppose
belongs to A, so even F square will belong to A, no?
Yeah, it's just a function from f to f. It's fine.
no. So suppose f sends s to like every element to one.
Fine.
So like now the domain of f square is the set one only. No, it is
Yes.
not defined. It is not defined on every element of that set S.
It is. It takes everything to one. So what's the issue?
Okay. Yeah, I got confused. Now it's cool.
Okay. Now, if we do this, then f of 2 and f to the 2n plus 1 is not equal to f to the n plus 2. We know this. Does anyone see why this is helpful?
Can you please set or auto compile?
Of course. My bad.
And look at cycles of F, cycle length of F.
This is actually just enough. We don't need to look at much. Important thing is this.
Okay, so we'll get some cycles.
Yeah.
Yes. Now there can be two things. That either f of t equal was t, so we could not place f to the n because f to the n was bad, right? If f of t is not t, then we can place f to the n, whatever it for whatever value of n. Correct?
I
Correct.
didn't get you.
Okay. If f of t, any t, and we can do this, do place G equal. So we may not be able to. Is this fine?
Why otherwise? Why we may not be able to?
Because then a G might be equal to, sorry, f to the n might be f.
Okay.
Okay. Now that we were able to do this, because f of t is not t, we're assuming f of t is not t, so we can do this. Correct?
Yes.
Okay, for large n, of course, like n greater than 1. But okay, now that we did that, can you see that f eventually has a period? Like any finite, if you're taking a finite set and applying a function to it, it will eventually have a period if you go deep in deep enough.
Yes.
Yes. Okay. So this is how you see it. This is how it helps you to visualize the basic idea. Mhm. Okay. Where's the vector tool?
Like here is it lines above. Yeah, here is it.
Oh, okay, fine. Now this is a random function, right? You took A, it went to B, B went to C, C went to D. And this is just for you visualizing. This is how your function is going. But eventually it comes back to something. Now you're stuck in this cycle, correct? So everything in this part has this, eventually has this period. The period length of this cycle.
Oh yeah. So we can take the LCM of all the periods.
Now, since every term has a period, you can take the LCM of the periods and look at a large enough term when everything is periodic. Great. Now, let's say K was the eventual period. And everything is periodic after.
Can you repeat that LCM thing?
Yes. Okay. Every term now has a period, right? A has a period, B has a period, C has a period.
Yeah.
But now there might be something. This is a period of what? Length 7.
Yeah.
But there might be something here which is period 3. So the period of the function is 7 into 3, right? 21. So I can take the LCM. After 21, the whole function is also periodic. Yes.
Okay.
So K is the eventual period, and let's say it happens, let's say periodic after J steps. Now just pick n minus 1 greater than J such that K divides J. Sorry, K divides n minus 1. If K divides n minus 1 and n minus 1 is greater than J, then f of n plus 2 must have been equal to f of 2, f to the 2 n plus 1. So done. That's it.
Can you repeat this argument?
Period is J. Sorry, period is K.
Yes.
K divides n minus 1. So n minus 1 is also period.
Yes.
So if I apply f to f n minus 1 times on f to the n plus 2, it must be f to the n 2n plus 1. But since it was periodic with this period, it's the same function. So we're done.
So what is the use of J in that argument?
It must happen after a certain number of steps, right? It's not directly periodic.
Okay.
Like A is not periodic right now. It's periodic after 4 steps. Like this must be here, 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 here. I did a million things, then I arrived here. I
But
eventually have the period.
like there's a cycle of 7 and there's a cycle of 3. Now the periodic of the function is 21.
I mean, if a period, if you look after 21 terms, everything has come to itself, right? The 7 thing has come after 7 steps to itself, then 14 steps back to itself, then 21 steps also it's back to itself. Everything is back to itself.
Okay, that way, okay, fine. It's fine.
So it's a
Oh.
period.
So in this, the one ABC one, like the period is 7, right? Even
Sure.
after some steps. But like after infinite steps, A doesn't come back to A.
We're not saying A comes back to A. We're saying after some steps, it's periodic. Like after
Okay.
after 10 steps, and then every 5 steps, it's coming back to the same thing it was coming to after 10 steps.
Yeah. Okay.
It's coming out to D, right? After every 5,
Yeah.
every 7 steps now. That's all we care about.
Yes.
That's the entirety of the argument, and that's the problem. Did everyone follow? So like arrows is this visual idea, like how you think about such a structure. Yes.
Arrows are just for maps, I think.
Yeah, just a way of thinking, no? Like you were able to think A goes to B, B goes to C. Oh, this is a cycle here, so it's a period. So it helps you visualize stuff. That's all it is.
Yeah, right.
Like now you can think of let's say you had an injective function. If you had an injective function, you can think of it as a where's my vector thing on here? Then an injective function you can think of as a bunch of chains. And so on. Like you could think of it, an injective function now as a bunch of chains, right?
Yeah, okay.
Yeah.
Why can't these two meet? Like, why can't there be a cycle?
Yeah, sorry. Chains and cycles. My bad. An injective function is basically chains and cycles.
So what about the period of that chain?
Chains are not periodic by definition.
So what can we do in that case?
It's not related to this problem. Just saying in general.
Okay.
But
Yes.
then where will O comma H go, which have no end? Like,
I mean that if it's an infinite set, they just keep going. And if you have an injective function on a set to itself, then it's just a bijective function. So it's just a bunch of chains. Yes, it's more helping tool to think about than its theory. It's not theory. So if it's on a finite set, then it's just a bunch of cycles, an injective function. Okay. If on infinite sets, it could be just a thing that keeps going on. Bijective functions in general just are a bunch of cycles or infinite chains on both sides. But that's just too weird to think about. So let's pretend that's not the case. So yeah, bijective functions are a bunch of chains plus infinite things on both sides. No, you may be dealing with infinite sets and nothing like that. So like, okay, let's look at another problem, for example. We looked at an A3, let's go crazy and look at an even harder problem. let's look at IMO 2015 P6. Okay. Now this is the problem we have. Just understand the problem first. Take your time and just understand the problem. Sure. Sorry. Does everyone see the problem?
Yes,
Like everyone understood the problem?
the problem seems very weird, like the condition too.
Hey, it's a very nice problem. Yeah.
The point of starting from n plus 1.
What do you mean?
Like,
I mean, you're starting from you start from m plus 1. What's the issue with that? I don't know. You can start from m and you just increase n by 1.
like I'm saying that usually sums are from 1 to like.
The point is that you start eventually, that you do not want things to start right at the beginning for some reason that we don't know yet.
Okay, so some things should eventually become equal to b, otherwise we can exceed a value.
No, not necessarily, no, because like some things will be smaller than b, some things will be bigger than b. Smaller terms
Okay, I
will end.
misunderstood the modulus. Sorry.
Could you floor number 2? Yeah, sure. Odd number n by n minus 1 by 2 whole square. Sure, works. But not relevant to the problem, no? Like you can do that generalization, but I don't see how it will help you solving. Okay, so anyone who has not understood the problem, I can try explaining it. Okay, seems like everyone got it, so we'll start. Now you have some kind of structure, but like we don't really know how to handle it. We have only two real properties given to us. conjecture a crazy sum. Try to create a function that looks nice to you.
F of I is AI plus I.
Amazing. That's it. F of I is equal to AI plus I. We came up with this function. What properties does it have?
Injective.
Injective. What do we know about injective functions?
Oh yeah, the arrows you
change in
said.
cycles.
It's for only k less than l.
Injective functions we just saw, right? Either chains or cycles. Can cycles exist?
No, because it is on an infinite sequence.
No, because it's increasing. AI is greater than I. F of I greater than I. So f to the k of I greater than I, so it cannot have a cycle.
Oh no,
Infinite.
why is it increasing?
AI is greater than equal to 1.
So, but still it is not increasing. Like just
Yeah,
it's,
it might happen that a of n is f of n is greater than f of n plus 1 if a n is greater than a of n plus 1.
What?
like if you just take AN as 10,
Like it's not given that sequence is increasing.
We are given AI plus AI f of I is AI plus I, right? So f of I, by increasing I mean f of I greater than I. Not
Acha.
okay.
so it. I do not. Yeah. Sorry, my bad. I meant f of I greater than I. If f of I greater than I, no cycles. So only chains. How many chains?
Let me think.
Can we have infinitely many chains?
At most 2015 chains.
Brilliant. Why?
All AI are less than 2015.
Correct. That's it. There are at most 215 chains.
Why let
Okay, try to prove it.
okay.
At most 2015 chains.
Like in the most case, I don't think that there will be change.
What do you mean? I mean, there are only chains. What do you mean there will not be any chains?
Like, can we say like the density of each chain is like 1 by
Don't
2015 at most?
don't bother with that. You can say that, but don't bother with that, please. Make a clean argument. The argument is, okay, let's pretend there are 216 chains. Every chain has a starting point. Say maximum starting point is S. Now consider S plus 1. These are 215 values. Every function has at least one value in this set. Every chain has at least one value in this set, but there are 2016 chains. That's not possible. So
Why
these are
every chain has at least one value in this set?
because every chain has started before it, and you cannot skip over the entire set because you're adding at most 215. Like if you start before the set, you start at something less than S, and you add 2015, you'll end up within the set.
Like you
It's,
can't.
it's a 2015 length space, right?
Let me think just a second.
Yeah, sure.
Can't we do like this? Like there are only 2015 starting points, so there cannot exist 2016 chains because two will have the
We have to prove there are only 215 starting points. How did you conclude there are only 215 starting points?
Okay, we'll start with AI plus I. Okay, I was confusing with AI. Sorry.
Oh yeah, got it. They are this. This is right.
Okay. Anyone else who's confused why there are at most 215 chains?
What was the motivation of doing this? Like,
Oh, this argument S to the S plus 214?
yeah,
Just a very standard argument. I don't even know what to say about it. Like everything eventually is in some small set. Okay. Like every chain is going somewhere, right? And in every 215 length space, everything has to have something. The only issue is it could have started after the set. So you consider the into 15 length space, which is after everything has started.
Can you like explain again how we have like 200, 2000 chains?
I said at most 215. I did not say 215 chains.
Yes.
Yeah. So let's say there are 216 chains. Okay. Now all of these 216 chains have some starting points. Let's consider a point which is after all these chains have started. Now S to the S to the S plus 2014, every chain must have some term in this thing, right?
Yes.
But these are 2015 things.
Okay, got it.
Okay, great. Now we are very close to finishing. Guess the value of B.
You repeat what you said.
We are close to finishing. Guess the value of B. No. Guess the value of B. It's not independent of. It's
Average
not
of the starting points.
Dude, that may be insanely large, no? Because I can shift one starting point to be really high. I can make one starting point really high, so the entire average is crazy high, and make it more than 215. So that's just bad. Just guess what would make sense here.
1007.
No. Injective functions make chains and cycles.
The number of chains.
Yes, very good. Somebody guessed it. It's the B's number of chains. Yeah, okay. Why injective functions make chains? What else can happen? Just think of it. What can happen? Like you have a current number of things. If it's a cycle, you're just happy. If it's a chain, then where can the last thing go? It can go to either a new thing, or it goes to something which is already in the chain. If it goes to something which is already in the chain, that's a contradiction unless it's a cycle. That's it.
Oh, okay. We guess the number of guess that B is the number of chains. But suppose we had a continuity in a contest. How do we be like sure that it can be the number of chains?
Yeah. Okay. So why should number of chains make sense is basically the question, right?
Yes.
Let's pretend AJ was fixed. Okay. For everything, I say AJ is, let's say 2. Then how many chains are there? 2 chains, correct? And B also you want 2. In that case, you cannot have any other B, right?
I didn't get if AJ is constant.
Let's say AJ is constant. That case works out, right? Like if sorry, firstly, name yourself correctly. Hi is not a name. Secondly, if the doubt is there, we'll discuss it later.
Hi is not a name.
Like somebody has named themselves Hi and are asking questions without explaining on direct message. Sorry. Okay, so that's the idea. Let's say age is constant. Okay. Now, what if AJ was a constant? You would want B to be the same constant, correct?
Yes, to make the sum 0, right? Minimum.
Yeah. Now, if you want it to be the same constant, but like look at what the structure looks like right now. Right now, it's just AJ number of chains. If AJ was a constant, it's the same constant number of chains. So that's kind of a motivation. In even weirder structures, the number of chains seems to be a thing which controls how much AJ is increasing randomly. Does
But
that make
still,
sense?
isn't it tough to conjecture the change? Like this is the special case when AIs are constant. There are a lot of many other ways other than change to interpret, which are more natural.
Yeah, I'm saying even if it's weirder, B just seems like a good value. And it's a hard problem. It's not an obvious conjecture. No, it's an IMO 6. It's a good IMO 6. If AJ is fixed, then there are AJ number of chains. Not in general. You can see this yourself. The points where the chains start are just 1, 2, 3, 4, AJ minus 1, and AJ. That's it. Sorry. Okay. Here's now the number of chains is our guess. Can anyone do the algebra now? Can anyone try to do the algebra now, please? Okay, we were pretending there are 2016 somebody is asking why S should belong to exactly one of 2016 chains. If anything belongs to two chains, that does not make sense. No, it's an injective function, and chains by themselves, like everything is in exactly one structure. It's not in multiple things. That's a question from the chains part. Okay, when please ask the question when I'm doing that, please. Like, if you're struggling with something, just tell me to wait and explain it then and itself, because I want to discuss many things. Okay. Bi greater than L plus D, what?
Sorry, I meant BI is less than I plus D, where D is the number of chains. Right?
What's, sorry, I don't.
Like, so sorry, not BI, I meant like the function that we defined, BI is equal to I plus AI.
Yeah, okay.
So, no, I was thinking maybe this will be useful.
Where L and D are?
No, not L. I meant to say I. It got
Okay, and D is?
D is the number of chains.
Why is this true? I mean,
Because
sometimes it could be weird, no?
acha,
How do we do the computation? Fine. Okay, I'll only do one side of the computation. Okay, I'll not do both sides. Other side you'll have to do on your own. Like, there are two sides of the computation. This value is at most to if you remove the modulus, it's like greater than it's less than equal to 1007 square, and it's greater than equal to minus 1007 square. I'll only do one side. You can repeat the other side on your own.
Can we take the computation as an exercise?
Okay, good idea. Computation also in itself is not trivial. It's easy enough, but it's not trivial. The main idea was till now. What happened? Is there some issue?
No.
Okay. Let's look at some slightly easier structure now. I think throwing you into the deep end was not a very good idea.
No, it is nice to do hard problem.
Okay, great. Let's look at this problem now. Iran TST 2014 P7. This is a very comparatively easy problem. In the exercise. Okay.
So can you zoom in the right side?
Just a second. I'm just changing the environment.
So like this Iran TST problem, did you like have you done this before in a handout, or were you just attempting at random?
These I've done. These three I've done in hand. ISL I'd done before. I think. I don't know. I'm actually not sure, but I think I definitely did the Iran TST in the handout. Okay. Can please try to read the question. Like the question may be slightly confusing because it uses some ideas. Okay. Does everyone know what a tree is?
Yeah, in graph theory.
Anyone who does not know what a tree is? I may be too quick to assume that already. Okay, since no response, I'll assume that you know what a tree is. Please stop me now, because like earlier also I was getting questions which were very delayed. If you have a question, please ask at the time.
By tree, do you mean a binary tree, or it can be any degree tree?
A tree just means a tree, a graph with no cycles.
Oh, okay.
Are you sure?
Yeah.
A connected graph with no sign.
Yeah, my bad. Connected graph with no cycles. Okay. You're given a tree with with every vertex labeled from 1 to n. Now you're changing the labeling in a certain way. You pick an edge that hasn't been picked before and swap its endpoints. Now after you have done with every edge in a tree, there are n-1 edges. You can easily prove that. You can use tree has n-1 edges as an exercise. I'm not going to do this now. We get now in the end you'll get another tree, right? Let's say where the A label was, it now we have B label. So let's say f of A is B, and so on. This will be a permutation of the original labels, correct? So like you could again draw the thing we were drawing before. Like
Actually, I didn't even get the question. They were writing at the end that prove that this permutation contains exactly one cycle. Like, how are we like reading the permutation?
I'm explaining the question only currently.
Okay.
I'm not proving it. Don't. Okay. So yeah, what did someone say? A and B are sets of labels or individual labels. And individual labels. A is a label. some vertex was labeled A initially, at the end it's labeled B. So I'll say f of A is B. I'll draw an edge from A to B, and so on. If I draw all the edges now, this is one cycle. The question is saying the structure I'll get will be one single cycle. That's a problem.
Can you repeat?
Earlier, at some point A, like initially a point was labeled A, then it got labeled B. So I draw an edge from A to B. Similarly, B was labeled B, then it got labeled C, so B to C, and so on. I draw all the edges.
Okay.
And edges, what I'll get is a single cycle, not a bunch of cycles. That's your question.
Basically, it is proving F is periodic, right?
It's proving.
It is proving F is periodic.
No, it's saying that F has one cycle. F does not, like, it's saying this is not this case. It's saying this is one cycle. There are not multiple cycles.
Or
Exactly.
any labeling. Never mind.
What's the confusion? I'm just saying there's one cycle. That's the entire structure.
To be honest, I still don't get the problem.
Okay, and B equal f of A, we have to prove that f is pure. Initially, f is n cycle, maybe decreased by one every operation. Okay, don't try to be very fancy. This is a relatively easy problem. Just try to induct. Is A to B to A called a cycle? If A goes to B, then B does not go to A, is one implicit instruction you can make. But yeah, A to B to A would be a cycle. If it was possible. It is not possible by the problem. Prove a C, then f of C. No, that's saying periodic.
No, I fixed A.
Yeah, but you're saying A has a period of C.
So that's what the problem is asking, right?
No, I'm saying there is the entire structure. I've drawn all n points. I've drawn all n edges. The all n edges are giving me one single cycle, not many cycles. Just look at it in the visual. Think of it in the visual form. Don't try to formalize it that way for now.
So in this case, you are saying you like for 6, when n equal to 6, you are saying something like something like this should happen.
Yes.
Oh, okay. Now I got it.
For the ones who needed to relook at the question. Okay. Now let's just try to induct. Let's not think too much. Let's try to induct. This question is purely visual. It has like no steps involved. You just need to visualize it.
But that swapping thing.
I mean, as soon as you visualize it, you can write it. It's not hard to formalize, but to think of, you need to do it visually at least. Like, let's say this was a graph, okay? As soon as I do the action on this vertex, right? My thing gets divided into two graphs. One from C, one from B. Two trees. Correct? There's a tree from C and there's a tree from B. Like this remaining part is a tree, this remaining part is a tree.
Yeah.
After performing the action, the labels will switch also, right?
Yes. B and C get switched, but they are in two separate trees. Correct?
Yeah.
Okay. Now let's say by strong induction, this had a cycle and this was a cycle, correct? Fine.
Yes.
Both of them were cycles.
Oh yeah, so I think we are just done.
Yeah. Both of them were cycles. But what I did was I replaced Q and I replaced J in the beginning. So where Q was going, J is going now. Right, since I switched Q and J, after the end of the thing, if Q was going to R, now J is going to R. So I can remove this and I can make this. After the end of the thing, J was going to K, now Q is going to K.
In this case, like after 20 turns, right? 5 into 4.
I mean, does not matter, you can count it.
Like just for confirmation, I was.
5 plus 9, 4, 9, 9 things.
Oh, okay.
Yeah, okay. So this is also cycle, so we're done. Since you just merged two cycles.
Is there
What
any
if you like start
non-inductive?
on the end? Like then you're not breaking it.
I mean, then it's just a single cycle and you're just, okay, let me make that. If you start on the end, let's B was itself, A was itself, you have a cycle. A was by itself, right? You switched K, J and K. So J is going where K was going. Where's my arrow? Where's my arrow? Yeah, sorry. J is going where K was going. But K and J got switched. And since J was by itself, K goes to J. This gets deleted, your thing. Cycle. Okay. You can think of there's a self loop on J there. And this fixing just works.
Is there any intuitive and non-inductive way to think of this? Because like induction worked, but I didn't get why it worked.
I mean, I don't know. I like the only thing I tried on this problem was induction, I think. Like it's you're given a very easy structure to work with, no? Like you're given two cycles basically already, if you assume the claim, and then they have to somehow merge. That has to just work almost, if the problem is true.
Okay. So is there a similar some other solution of this problem? Are you aware of some other one?
I don't think so. But you can check the thread, obviously. Maybe there is. I'm not aware of any. I've seen a couple solutions, but all were basically this, just worded or something like that.
Okay.
Please, if you find some other interesting solution, do tell me as well. Just ping me on the
Okay.
server and tell me. Okay. I think now you should be getting the hang of what arrows were supposed to mean and how we are doing. Yes, after every operation, two cycles merge into one. Kinda, but the thing is, we first did the first edge, and then we pretended that edge was never there. Let the remaining things happen, and then we were like, oh, that edge, but that edge was there. They should have been together. The two cycles should have been one. Okay. So are you guys getting slightly comfortable with what arrows is supposed to mean?
Yes.
Okay, good. And how it's helpful visually. So one problem that I want you to try now is this.
I think arrow is just graph theory, maybe.
Arrows is a different way of thinking, but you're basically creating graphs if you want to say that. But arrows is not a formal idea. It's just graph theory is a proper idea. Graph theory is a proper field. A lot you can do about with it. Arrows is just a way of thinking or visualizing things. I guess. Okay, let's try this one now. I'll throw you in the deep end again. If you don't want, okay, let me actually give you a choice of a couple problems. That will make it slightly more interesting, I guess. Because I want you to see a couple of ways the idea helps you in thinking. Like all three examples we have seen till now are fairly different, I think. My population. These are from my problem sets. From my old problem set, I'm just copy pasting the statements from my other overlay file for the one who's asking. The problem set there I've shared before, no?
Which problem set?
As I said on my blog, you can find it, or on OMC. Arrow's problem set.
Okay.
And another way, good example would be this. Okay, we have three good examples. There's nothing much. It's just the blog is just for me to sure. Just keep my stuff. For the answer, doesn't the first condition imply f to the m of m is equal to m? It implies f to the m is divisible by m. F to the m of m is divisible by m.
No, like we have that. So the second condition basically says that fn takes all values except a finite number of values.
Fine,
So
sure.
we can take n to be very large, and so fm like f raised to m of m, like we can fix m, and we can take n to be very large. Then f raised to m of m should be equal to m. No?
I don't see why that's true.
No, so basically, like we have n divides. Oh wait, sorry, I misread the condition.
Okay, some people don't want to spoil a recent IMO 3. Good enough. Gone. My bad. I'll not spoil an IMO 3 for you. That to this one. And don't worry, knowing its arrows does not change anything. Or related to arrows does not change anything about the quality of the problem. And I think this one. Yeah, okay, pick. INMO SL. Okay, let's do INMO SL. INMO SL first. Now you're given a definitely very iterated function, which motivates you to look at what happened now. I mean, we already did a P6. So no reason to be scared of N8s. No, Atul is used to this by now. Okay, so
These zoom in, it's difficult to see the powers.
You can close that thing on the left, so you get more space to write. And no, like I mean the thing.
yes. Good idea. Nothing. He's done nothing. It's just a joke. Don't worry. Okay, let's look at this problem. Since people want the INMO SL, since it looks relatively easy. Okay. So what does the problem seem to tell you? What does the problem seem to tell you? Let's stop this, please. Please. Yeah, okay.
What is this notation after f of n? There is a small n in subscript in brackets.
F to the f. This f of n is some value. You apply f of n that many times on n, and then you apply that whatever value you get again on n that many times, and you eventually get n.
I still didn't got the question. Can you tell what is it for, say, n equal to 2?
The problem, I mean, it's just saying f to the f of n of n of n is equal to n. So
Oh, okay, got it now. Got it. I got confused.
I don't know what problem you are referring to, but don't worry about what other problems are there. Just look
It's
at.
the f of x, f of y thing.
Okay, leave it. Don't worry. Anyway, what does this tell you? Visually, again, back to the visual thing.
The cycle is of length in the power.
The cycle divides length of the cycle divides the thing in the power. Great. So the period, there's a term within the cycle. This thing is within n cycle of n, right? There's a thing within the cycle that is divisible by the period, right?
I didn't get you.
F to the f of n is some term in the cycle of n.
But yeah, it is equal to n. We are given that.
No, this much. Like just the amount I've highlighted. Isn't the highlighted amount not visible?
Yeah, it is visible.
Yeah, just this amount is in the cycle of n, right?
Yeah.
I mean, by definition, like it's f applied sometimes, so the cycle, it does not move out of the cycle since n is in a cycle.
Yeah, the length of cycle divides this number.
Yes, amazing. Length of cycle divides this number, and this number is also in the cycle.
Let me think why. Yeah, it is in the cycle, of course.
Yeah, right. So if so, you got that there is a term within the cycle that is divisible by the cycle length. So what should you plug now?
There is a number in the cycle.
That is divisible by the cycle length. This is a
So
number in the
m equal
cycle.
to 1.
What?
So we should plug 1 maybe then.
No, don't plug anything. There's something in the cycle that's divisible by the cycle length. You want to plug something, but like dependent on this cycle, right? You just don't want to plug in arbitrary things. Dependent on this cycle, what you want to plug.
F of n.
Okay.
Maybe we should plug that number which is divisible by the length of the cycle.
Why would that be good for us? I mean, why is it in the cycle? Yeah, exactly. It's f applied sometimes, so it's something in the cycle of f. It does not matter what k is. Exactly. So let's say this was the cycle. Now, if you were plug in a, I have told you that j is something that's divisible by the cycle length, right? Now, what do you want to plug so that this value just crumbles apart somehow?
J.
How do you talk? What do you know about k? You know nothing about k.
Not K,
Oh,
J.
I.
If you plug in j, then f of j is k, right? K you don't
We
know.
should plug I, the thing before J.
Exactly. As soon as you plug I, what happens? This term becomes divisible by the period. This is j. So it spits out I, right?
Oh, so n equal to I.
No, I is also divisible by the period.
Let me think.
N equal I. You got f to the I of I is I. So I is also divisible by the period. You plugged in j. J was divisible by the period. Sorry, you plugged in I. This term was j, right?
Yeah, so f of I is equal to I.
F to the j of I was I. So f to the I of I is I. So I is also divisible by the period. Yeah, basically plug in f to the no, not of a random term. We are plugging in the term which is divisible by the period, the term before that.
Okay. And this holds for that term.
Yeah, so if that means this term is also divisible by the period.
Oh, so this means that all the things in the period are divisible by the length of the period.
Exactly. All the things in the cycle are divisible by the length of the period. Because the thing before is also divisible. Do you see why? Do you understand? Does everyone understand?
Yes.
Can you please repeat again how I is also divisible by the line?
You plugged in I, you got j.
Yeah.
This is j, right? F of I.
Yes.
But f to the j of I must be j because I is in the cycle, and if you apply j is divisible by the period of it,
Yes. It
so
should
you'll
be
get
I.
back I.
Okay,
So
I
you
did
get
right.
f to the I of I is
Yeah.
I. So I is also divisible by period. Everything in the cycle is divisible by period. Now that's it. So find all m for which every saturated function has the property f 2014 m is m. right? This is all that's left. So just make
Factors.
nothing, just like all factors of 2014. Yeah, all factors of 2014 work, because yeah. Now the only thing left is, what if it's not a factor of 2014? Can anyone just do that?
I'm not sure why all factors of 2014 work.
This period, in the period of the cycle, a factor of 2014 would be a factor of that, which is already a factor of 2014. Let's say I had a period P, then P divides I. That's what we proved, right? But I divides 2014. So P divides 2014. So
Yeah.
2014 is also a period. So done. So all factors in 2014 work.
Got it.
Now the
We
only
also-
yeah, sorry, go on.
No, I was just going to say we need to construct a function that shows other things don't work.
Yeah, can anyone just do that? It's not very involved or anything. You have a very structural thing that you need. Let's say the number was m. M was the number which is not a factor of 2014. Then we create the following function. M goes to m goes to 3m maps to m square event c dots m square maps to m, and that's it. That works. Period of everything is m, and m is divisible. Other things are identity. Not in this set. Go to themselves.
And why can't we do this argument for m equal to 2, say?
If you do that, then 2 and 14 is a multiple of 2. So since 2 is the period, 2014 is also a period. You just proved it, no? Like all like period of I divides I, right?
Yeah.
But if I divides 2 and 14, then period divides 2 and 14. But then I must go to itself in 2 and 14 steps.
In a contest, do we have to show the working for that this function works?
I mean, you just write if I is in the function, and then f of this stuff is divisible by m. So since m is the period, this goes to itself. If for others, since their identity, whatever times you apply, the number will go to itself, so it's fine. This argument is fine. No, I don't think there's any issue in this.
Yeah, fine.
Fine for everyone. Yeah, okay, great. Now you have to choose N6 or N8.
6.
Eight.
And
N8.
it is kind of impossible. Like not impossible, but
My conjecture is this is somehow related to 6 less than 8.
6 less
Okay.
than 8.
Okay, N8 seems to be winning. Sorry.
Okay.
Okay, so let's look at the N8. Confidence. I like this. This could, you guys have a lot of confidence.
But it might happen that we just end up wasting time.
It's fine. Don't worry too much about how much. Try to enjoy it a bit more. It's fine. Slight time waste is fine. You don't have to be optimal about everything. Okay. So let's read the problem because I've also forgotten it. Somebody. Yeah, okay, I'll refer to my notes while you read the problem.
You stopped this finish.
Yeah, I'm aware. Was it visible where I was going?
No.
Just just the Google Chrome was visible, right?
In fact, the overlay 5 only, yes.
Yeah, good. Still give me a minute. I'll open it. Okay, how many of you are familiar with QRs and all?
Yes.
Okay.
So QR is a hint for this problem.
Sure, you can take it as such.
Can you show the screen share? Like your.
Right, of course. Yeah, this one, right. Okay. Okay, leave it. Why? What's the need for notes? Let's just solve it. Come on, stay confident.
So if AI is even, then the next thing has to be a QR.
Okay. That implies
That exactly P minus 1
But
only.
okay, some
this
people
is
are not familiar with quadratic residues. Okay, let's do the N6 then. I'm not going to
but this
explain.
is like this also has cubic residues and all that, not only quadratic.
Yeah. That stuff is needed. It needs some theory knowledge.
Does it need knowledge of cubic residues?
Huh? Yeah, slightly.
Does it need? Oh, yeah, then N6.
Okay. N6 does not need any theory. Let's try it. Okay, so what do you understand from the second condition?
F has a finite range.
What?
F
Does
of
F
n has
have
a
a finite range?
I mean, f of n is what? I don't like. Can you eventually all be on the chain?
I think
And second
cycle.
condition implies that F has a finite range, right?
It
Finite
says
range?
F.
No. What?
It
No.
says F's range is everything but finitely many numbers.
Oh, wow. Fine.
doesn't this imply like for there exists a m such that for any I greater than m, it has a pre-image in the set.
Yeah. And what does the first condition tell you?
How, like, what were you saying about interpreting the finite condition?
Not much. I was just asking, how would you interpret it?
So is this I think most probably the interpretation is union of cycles. Is that right?
There's no, Howard. Not exactly. No.
Why union of? Oh, okay, it is not injective or something like. Fine.
Okay. First condition. What does this tell you? N equal 1.
F of m is greater than m.
Great. That's
Can you
good.
repeat?
N
So
equal
no
1.
cycles.
No cycles. Exactly. N equal 1. N equal 1 tells you f of m is greater than m.
But then can't the set Fn and greater than 0 be finite?
Why not?
If it is finite, we can choose its largest element, which is k. Then f of k will be greater than k.
I think you are misunderstanding. The second statement is saying that f has all but finitely many things, not finitely many things. Second thing is saying f of n has all but finitely many things. It's saying z naught, not including f of n, is finite. If we,
Okay.
not f of n is finite. Oh, we are running out of time. Okay, I'll extend for 10 minutes or 15 minutes. Yes, a
Do
lot
we
of
have
the,
any class from 9 to 10?
no, people have some games planned and I don't want to spoil those activities. Don't worry, it's fine. We have enough days to solve N6 and other problems. Don't worry, this will not be the hardest problem that you'll solve over the course of my lectures at least. Yeah, F injective. How did you get F injective? N divides F to the N minus A, F to the N B minus B, N divides B minus A. Correct, almost. It's correct actually. What almost? Yeah, it's correct. Does everyone see the argument of injective?
Has
It's, somebody has put it in the chat.
So how does large n matter?
Yeah, got it.
N greater than B minus A implies you just take N greater than B minus A, right? But N divides B minus A, so B minus A is 0. So equal B, so injective.
Oh, we assume n divides b minus a. Yeah. Oh, okay, never mind. Yeah.
Yeah, okay, great. So now we have injective, we have no chain, we have f of n greater than n. We have that the starting number of things is finite. What does this tell us?
Why is there no chain?
I never said there's no chain, sorry if I did. Bunch of chains, correct. Finitely many chains, in fact, because this is the claim. If there are infinitely many chains, that would mean infinitely many starting points, which is just not true.
I so why not cycles?
Because f of I greater than I. So f to the ki greater than I. But if f to the ki is equal to I, that's just not possible.
And why can't there be infinitely many chains?
Because every chain will have a starting point. There's no infinite chain in both directions because it's z greater than 0 and f of n greater than n. So every term in the chain before it is smaller than the next term. So every chain has a starting point, but there are only finitely many starting points from the second claim.
Why does the second thing imply only finitely many starting points?
That's literally the claim, no?
Can you show it once again?
Pre-image of, like, if you remove image of f from z greater than 0, the number of things there is finite. So it's a bunch of chains.
Um, but it could be something like 1 to 3, 3 to 5, and 2 to 4, and 6 to 7, or something like that. This goes on.
I mean, everything goes to one thing. That's like a property of a function. No, you cannot have this structure.
Can you repeat?
I mean, you know that it's a bunch of chains, right? The only problem is infinitely many chains, right?
Hmm.
Okay. So every chain has a starting point. Also, you got
Hmm.
every chain has a starting point. Then the starting point of every chain does not have a pre-image, like does not have a pre-image, right? Because that would imply
Oh,
this
got
goes
it
to
now.
this.
Got it.
Yeah. Okay. Cool. Finitely many chains. What else?
Now maybe we have to use the first condition even more.
Good. How? Currently, are you able to see the GeoGebra?
No. Yeah, now I can.
Okay, good.
Can you show that only once?
Problem statement?
Yeah.
Okay,
Let
sure.
me copy it down.
Okay, sure.
Yeah, you can go to GeoGebra.
The problem asks to prove that each chain is an AP.
Great. Very good. Does everyone see this claim that Atul just made?
Can you
Can you please
repeat what he
repeat?
said?
Atul, please repeat what you said.
The problem is asking you to show that each chain is an AP.
Each chain is a AP.
Like, because problem says difference between the next term and previous term is constant.
मैं समझा नहीं.
He's claiming that the problem is equivalent. This claim that f of 1 minus 1, f of 2 minus 2, this claim is equivalent to the chains being an AP.
Chains being an AP.
Every chain is an AP, he's saying. A, B, C, E, F
Everything.
is a chain. He's saying it must also be an AP.
So can you tell how did he reduce to that?
Atul, do you want to explain?
Oh, like f of 1 minus 1 is just like the term in front of f1 in the chain minus like 1. And we want to show that's constant. So like difference of adjacent terms in the chain, we want to show is constant, which is AP.
Yeah, I got it.
I still didn't get.
Atul, try more.
Basically, like you just want to show the difference between any two terms in the chain is some constant. That's what an AP is. And that's exactly what the problem is saying, because f of something is just the next thing in the chain after the term. So since the problem asks you to show that f of something minus that thing is constant, it wants you to show that difference of the next term in the chain minus previous term is a constant.
No, it is saying periodic, not constant.
I misread the problem.
Good. But the claim is correct. Every chain is an AP.
Okay, so let's now try to prove the claim.
I would recommend focusing on the lecture. Okay. Oh, Atul has done this many times. Yeah, let's. I'll try to finish by 9:15 or 9:20. and then you can go for Hanabi. Sorry for delay.
I think what we can do is that one who want to go for Hanabi can go and they can watch the recording later, and others can stay if they don't want to go to Hanabi.
I mean, that's just not good. No, like if the camp is having activities, anyone who's participating in the activities should not be penalized or something. Oh, I'm not going to play. No. Let's focus on the problem, not on wording. Yeah.
Can you give this N6 as an exercise?
I think we are very close. No,
Acha.
like just try for 2 minutes. Nobody here is making brave claims, is the whole thing. Like, make a claim that, okay, we can just conclude that this chain works somehow.
Like you consider any chain and you consider the consecutive differences, like they be a1, a2, a3, and so on. But then by the given hypothesis, we know that 2 divides a1, 3 divides a1 plus a2.
Okay, sure.
Oh, sorry, I said wrong. 1 divides a1, 2 divides a1 plus a2, 3 divides a1 plus a2 plus a3, and so on.
Sure.
So most probably this should be enough to give a AP. Let me see.
Sure, yeah, that's equivalent, but why? Why is that true?
I got that AI is congruent to A of n plus I modulo n.
What?
Oh, sorry, maybe no. Sorry.
So is the common difference of all the chains, like all the APs same?
Doesn't matter. Also, no. Because you can set up every chain with some common difference and it's fine.
Oh, okay. So suppose two different chains are there. They have different common difference. Fine. Now,
Array, just a second. Any chain you have which has this property that it's an AP satisfies problem conditions.
Yeah.
Do you see that?
Yes.
So if there were a bunch of chains with different common differences, then they also have to work. Then the problem must still be true, no, whatever's happening, because that just satisfies the two given conditions. So it has to satisfy the third as well. So it's fine. Just try to prove that it's an AP. Come on, come on. It's not that bad. What's good for divisibility conditions?
Primes. Oh yeah.
Yay, primes. Let's do primes.
And take N to be time.
Great. N is equal to P.
So we get for if we fix M, then for sufficiently large prime P, we have that the so the period should be equal to P.
Uh,
I mean, no, sorry.
yeah. Not the period should not be P. That just is.
No, no, no. My bad.
So are we fixing M or fixing P?
M.
He's saying let's pick a large prime P.
Oh,
Okay, let me put it this way. Instead of concluding that every chain is an AP, if you prove one chain, and then if you just inductively prove like if you have some set of chains, then another chain will also work, and so on. If you could do, then that's also fine, right?
like if one chain is in AP, then we can use the analogous argument for others.
Maybe the argument requires it. Maybe it requires some special condition, no? Like I'm saying, maybe at least one chain is an AP you could prove. Remove that and try to repeat the argument for that.
Oh, maybe you are talking about the chain starting with one.
I'm not saying anything.
Like
No,
you're hinting.
like the first element of the chain clearly does not matter because you can shift any chain. Like if the first chain is starting from n and the other chain is starting from 2n, I could shift the 2n chain to n, decrease every term by n. This chain I increase every term by n. It's still fine. Sorry. Yeah. Yeah, okay. So how do you do this?
Just 2 minutes.
Okay. Okay, why should it even be true? Like, why should every chain be an AP? Why does that make sense to you?
Because if it is a AP, then the conditions are trivially satisfied.
No, but why should it be an AP?
I didn't get the question.
Like, I agree that they're APs, but why should they be APs? Like, why can't they be slightly random? Why should every chain be an AP? From the two
Oh,
conditions, why should it be true? Like, why does that intuitively make sense? Let's say it was not an AP. Just think of it mentally right now. Let's say I increase by 2 first. Then I increase the next term by, I have to still satisfy the two things. So I have to change by an even number.
4 say.
Now you have gone by 4. Now again, now I have to satisfy divisibility by 3 and divisibility by 2.
So maybe you take 6.
So you have to pick 6. Now again, this thing keeps getting larger and larger and larger, right? This way maybe. Like you have so many conditions to satisfy that the number you are asking for might get very large. The next difference. Make sense?
But if you have too many large differences, you won't fit all numbers in finite chain.
Exactly. If you have too large the differences, you'll not be able to fit it. You have to fit every numbers into a finite number of chains. You'll not be able to do that if differences get very large.
How to formally like conclude that?
That's your job right now, no? Okay.
Telescoping kind of thing may work. Like we can replace m by f of m and then by f of 2m. Like if we call the difference between the two consecutive terms as x, like if f of p f of p plus I of m minus f of p plus I minus m I minus 1 m is xi. So we'll get that like we can telescope and we'll get a bunch of things add to something which is divisible by p.
Okay. Interesting. Oh, so why not something like 2 4 4 4 4 and others being constant? 2 plus 4 is already 6, and the next difference you want with 2 plus 4 plus that difference should also be divisible by 3, which is also an extra condition you have come up with at this point. So that also is So your new number is also divisible by 3. And constants, obviously.
I think we should assume there are T chains,
Okay.
and then we can say that there's some difference is less than equal to T
Some difference is less than equal to 3. Sure.
consecutive,
Sure. Okay, sure.
but that maybe doesn't help because one divides everything.
Okay, also I think at this we are close to a point where we should be ending. Yeah, okay. I think we are at a point where we should be ending now. I'll leave this as an exercise. Try to send me a solution if you solve it.
Okay.
This is an exercise. Yeah, and this requires some theory, so I left it, but try to do this problem. And if someone can link the handout, that's great. Otherwise, I'll send it afterwards.
Which handout?
Just the problem set.
Oh,
Atul just linked your blog in the chat.
Yeah. Also, I'll add a problem because add a problem in that, and then you can.
can you send these notes in the Discord, like
Yeah. Okay. I'll send this as well, and the
the
others.
previous?
Yeah. Okay.
Thanks for the class.
Yeah. No
Bye.
problem. Hope you enjoyed. Bye.
Bye.